the kinetic molecular theory explains all of the gas laws. So it's really important to understand the kinetic molecular theory in order to understand how gas variables relate to one another. So there are three postulates to the kinetic molecular theory. The first one deals with the word kinetic meaning motion. And so the first postulate is that a gas is a collection of particles in constant motion. These particles move in random straight lines until they collide with something. So they can collide with another particle or they can collide with the walls of the container, and then they just go off and move in another straight line. These collisions are elastic, meaning that no energy is lost or gained in the collision. So the particle goes into the collision with the exact same amount of energy that it comes out of the collision with. The second postulate of the kinetic molecular theory is that the size of a particle is negligibly small. Gas particles are in an extremely low density state. They are very, very, very far apart. So far apart, in fact, that relative to the space in between them, we can say that the size of an individual gas particle is basically zero. It's not zero because it's matter, it has mass, it takes up space, but it's so small compared to how much space is between the gas particles that we can say it's negligible, meaning for us that the identity of a gas doesn't matter. It doesn't matter if it's a particle like hydrogen or helium or a big particle like xenon or a diatomic like chlorine. The identity of the particle doesn't matter. All of these gases are going to behave the same way. Lastly, average kinetic energy of a particle is proportional to the temperature in Kelvin. Kelvin is Celsius plus 273. And the energy is only proportional to the temperature Kelvin, not the Celsius temperature. So for all of these gas laws, anytime you're dealing with temperature, you do have to convert the temperature to Kelvin to be able to use it. Pressure is the amount of force per unit area. Gas pressure comes from collisions between the gas particles and the walls of the container. As those gas particles collide with the walls of the container, they exert force on the walls of the container. So that is the pressure. More collisions, more pressure, fewer collisions, less pressure. Particles colliding with one another, like gas particle to gas particle collision, does not cause pressure. It is only collisions with the walls of the container. Standard pressure is the pressure of the atmosphere at sea level. So all of these are standard pressures. They are all equivalent to one another. They're just different units for pressure. So kilopascal, standard pressure is 101.3, PSI is 14.7, etc. Since these are all standard pressures, they are all equivalent to one another, you can use them as conversion factors when converting between one unit of pressure and another. So if I have a bicycle tire inflated to 132 PSI, that seems like a lot. What is the pressure in millimeters of mercury? So 132 PSI, we're going to cancel that unit PSI, and we're going to convert to millimeters of mercury. We're going to go back to this table and use our standard pressures as our conversion factor. So 14.7 PSI equals 760 millimeters of mercury. This is going to give me 6,824. I can only use 3 sig figs because there's 3 sig figs in PSI, or in the 132, so 6,820 millimeters of mercury. Going from atmospheres to kPa, same thing, 0.997 atmospheres. Cancel atmospheres, go to kPa. Using my standard pressures, standard pressure is 1 atmosphere, standard pressure is 101.3 kPa, so I can use those as a conversion factor and get 100.99. I have to, again, use 3 sig figs, so that's going to round to 101 kPa. When you have a mixture of gas, each gas exerts a partial pressure, a fraction of the total pressure. So partial pressure is pressure due to any individual component in a gas mixture. And Dalton's law of partial pressure states that if I have a mixture of gases, the total pressure of that mixture is equal to the sum of the partial pressures of the individual gases. So for example, if I have a mixture of helium and nitrogen, the pressure of that mixture is equal to the pressure of the helium plus the pressure of the nitrogen. Using Dalton's law, we're going to use that guess method, given unknown equation, set up, solve. I am given a total pressure of 0.97 atmospheres. I'm given a pressure of carbon dioxide. I'm given a pressure of nitrogen. Unknown is the partial pressure of oxygen. Equation is Dalton's law, so my total pressure is going to be the pressure of the carbon dioxide plus the pressure of the nitrogen plus the pressure of the oxygen. When I go to solve this, notice that both the total and the carbon dioxide are given in atmospheres and the nitrogen is given in kPa. They have to be the same unit in order to add them. It doesn't matter what that unit is. If you wanted to make them all millimeters of mercury, that's fine. They have to be the same unit, though, to add them. For simplicity's sake, I'm going to just convert the 12.16 kPa into atmospheres. So 101.3 kPa, 1 atmosphere. That's going to give me 0.1200 atmospheres as my pressure of nitrogen. So 0.97 atmospheres equals 0.7 atmospheres plus 0.12 atmospheres plus the pressure of oxygen. Solving that, you get the pressure of oxygen is 0.15 atmospheres.